Okay, for what we will be looking into will be non-integer exponents and radicals. And we're fresh off of looking into integer exponents. Now, in terms of translating what we have in the case of non-integer exponents and putting in the context of radicals, we have, just as one of our properties, we have a raised to the m over n degree, and that is equal to the nth root of a to the m and we can say conversely that the nth root of a to the m is equal to a to the m over n degree. Now, for what is regarded as n, this is going to be what is referred to as the index of the radical. Now, we will eventually be looking into simplifying the radicals of various types. But let's say that if we're just looking at interaction between non-integer exponents and radicals, and we will say that in the first case, we'll say that we have x to the 2/3. Now in this particular instance, m is represented by 2, n is represented by 3, and the denominator defines the index of the radical. So we'll end up with a cubic root. And for this particular instance, we have the cubic root of x squared. And let's say that just taking a page out of the product to a power property. Say we have a couple of variables, m and n. Say we have m times n, and we have raised to the 7/4 degree. Now, if we remove the parentheses, we have for m, we have raised to the 7/4 degree. Likewise, n is raised to the 7/4, and we convert this product into a radical. So we have for m to the 7/4, we have the 4th root of m to the 7th, n to the 7/4. We have the 4th root of n to the 7th. And anytime you have like radicals, we can squeeze the terms together under the same index number. So we have, in the product, we have the 4th root of m to the 7th times n to the 7th. Now, technically, this radical can be reduced, but just in conversion terms, using this particular property set, we'll just leave this as the 4th root of m to the 7th times n to the 7th. Now, let's say if we have an integer, and we will say that we have 36 raised to the 1/2 degree. So technically, m is at 1, n is at 2. And for the nth root of a to the m, we have the 2nd root of 36 to the 1st. Now, typically, you will not see the index number 2 in many samples because 2nd root is just in reference to square roots. And here we have the square root of 36 and that is going to be equal to 6. Now, let's say that if we cross over to what will be referred to as simplifying radicals, and let's say that just start us off. Okay, say we have in the case of the family perfect squares. And we will say that we have among the first natural number perfect squares, we have 1 times 1 is 1, 2 times 2 is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and we'll just take the first 10 natural number perfect squares. 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, and 10 times 10 is 100. And let's say that if I'm looking at simplifying the following. And we'll say that we have, in the first instance, we'll say that we have the square root, and we'll say we have x to the second, y to the fourth. And if I go from, say, just a gradual conversion from radical to non-integer or integer exponent ultimately. Okay, so you have the square root of x squared, y to the fourth. And if I go from radical to exponent, so we have x to the m over n. So that's going to be x to the 2 halves. Y to the m over n, your m value is going to be at 4. N is at 2. Again, that is the index number. And guess what? We have x to the first and y to the 4 halves. That becomes y squared. So the square root of x squared, y to the 4, that reduces to x, y squared. Now, and let's say that if we have the square root, and say we have of x to the 6th, y to the 12th, z to the 9th. So again, still working with square roots. So we got the square root of x to the 6th, y to the 12th, z to the 9th. Okay, and if you notice, okay, if we look at what we have here, so we have 6 is an even number, 12 is an even number, however, 9 is not. And let's say if I do what is referred to as a bit of factoring. Okay, and in this one case, you have, so you got x to the 6th, y to the 12th, and without going over y to the 9th, now the highest even power that is under the degree of 9, okay, it's just going to be 8. Okay, and so for what we have in the mix, okay, so if I separate, okay, the perfect squares apart from the factor that is not a perfect square, okay, so I have essentially looking at second roots. Okay, so I have x to the 6th, y to the 12th, z to the 8th. I got times the second root of z. And for what we have in the process, okay, so we have x to the 6 halves, y to the 12 halves, times z to the 8 halves. And now just for the radical, we say the second root of z is just simply the square root of z. And for what we have in the reduction, okay, so we have x to the 6 halves, this will go to x cubed, y to the 12 halves will be y to the 6th, z to the 8 halves becomes z to the 4th. And then tagging along, we have the square root of z. So that would be the simplified radical form of this particular square root expression. Now, if we have, let's say, the square root, and we have 16, x to the 6th, y to the 8th, and z to the 10th. Okay, now 16 is a perfect square number, and in fact, x to the 6th, y to the 8th, z to the 10th are perfect squares. So we have, in essence, so we got square root of 16 is going to be 4. Square root of x to the 6th. Okay, so you're looking at, in essence, again, square root, you have second root, so you have x to the 6 halves, y to the 8 halves, and z to the 10 halves. And in the reduction, okay, so you got 4 x cubed, y to the 4th, and z to the 5th. Now, let's say that if I carry this over to perfect cubes. Now, we have for perfect cubes, and so we have in the natural numbers, okay, so 1 cubed is 1, and 2 times 2 times 2 is going to be 8, 3 cubed is going to be 27, 4 cubed is 64, and 5 cubed, we have 5 times 5 times 5, which will be 125. And so we'll just leave it at the first 5 natural number perfect cubes. Now, and let's say that if I were to simplify, and where I had square roots earlier, let's say if we work with cubic roots. Okay, so we have the cubic root of x squared, y to the 4th. Okay, now, if you notice, for x, the degree to which x is raised is smaller than what we have for the index. Now, for y to the 4th, not a perfect cube. 3 is not divisible into 4, but I can nonetheless factor out a perfect cube from y to the 4th. And in factoring, we have y to the 3rd times y. And we have in the mix, so if I have, let's say, the cubic root of y to the 3rd, and I have times the cubic root of x to the 2nd times y. And if you notice, we have for y to the 3rd, taking the cubic root of this, so you have y to the 3/3 times the cubic root of x squared y, cubic root of y to the 3rd, this would just go to y to the 1st. And so we have y times the cubic root of x squared y. And let's say that if I have the cubic root of x to the 6th, y to the 12th, and z to the 9th. Now in this case, we have 3 is divisible into all of 6, 12, and 9. So we have in the reduction, so we have x to the 6/3 times y to the 12/3. And we have times z to the 9/3. And in the reduction, so I have x squared, y to the 4th, times z to the 3rd. And let's say that working with not the square root, but the cubic root, and we have of 16 x to the 6th, y to the 8th, times z to the 10th. Okay, now if you notice, okay, 16 is a perfect square number, but it is not a perfect cube. And the highest cube that is divisible into 16 is going to be at 8. So you have a perfect cube with 8. And 16 we can factor out as 8 times 2. And 3 is divisible into 6. So we have x to the 6th. Now, in the case of y to the 8th, 3 is not completely divisible into 8. So if we factor out the highest perfect cube less than y to the 8th, we have y to the 6th. And this will be factored out as y to the 6th times y to the 2nd. And for z to the 10th, highest perfect cube divisible into z to the 10th is going to be z to the 9th. So we're going to have z to the 10th to factor out as z to the 9th times z. So if we separate what we have here, perfect cubes, we have 8, x to the 6th, y to the 6th, and z to the 9th. And we have with the others, have times the cubic roots, and we have of 2, y to the 2nd, and z. And so we got the cubic root of 8 is going to be at 2, and a little bit of history repeating itself. X to the 6/3 is going to be at x squared. And we have y to the 6/3. 6 divided by 3 is going to be 2. Z to the 9/3, we have z to the 3rd. And so we have for the final result in this one, we have 2x squared y squared z cubed times the cubic root of 2y squared z.